Hello again. Let us continue with number 7. So, for number 7, how long how long will it take for 16 grams of Ra226 to break down until only 1.0 grams remain? I'm sorry, that should be gram. Okay, so we are given the following. So we are given that A sub 0, the original amount, is equal to 16 grams, and the amount afterwards is equal to 1 gram. So we are not given the time or the time and the half-life. So what do? We go back to the question. It says here that how long. So you have to find t in terms of h. So using the formula, A is equal to A sub O times E raised to ln 1 half times T all over H. We substitute the following values. So 1 is equal to 16E raised to ln 1 half raised to T all over H. We divide 1 by 16 and we get the ln of both values. So ln 1 over 16 is equal to ln 1 half T over H and ln E. So ln 1 over 16 is equal to negative 2.77, while ln of 1 half is equal to negative 0.693. And we know that ln E is equal to 1. So 2.77, negative 2.77, my bad, divided by negative 0.693 is equal to 3.99. And we have to find t in terms of h because the question asks how long. So this would be equal to t is equal to 3.99 h. And because the given is 116 grams and 1.0 grams, my bad, it should be 1.0. 1.0 grams, okay. We have to follow the sig figs rule, and t is approximately equal to 4.0 h. So that is for number 7. Okay, now we move on to number 8. Now number 8 is a different kind of question. Let's see here, number 8. But let's read first the question. Okay, number 8. So now we're going to talk about nuclear reaction. So give the nuclear reaction for alpha emissions of polonium-210 and give the reaction for beta decay of carbon-14. Okay, so polonium-210. 210 here is the mass number of polonium, and mass number is equal to protons times, protons plus neutrons. Same here with carbon-14. 14 here is the mass number of carbon. And again, the formula for mass number is protons plus neutrons. So, okay. But first, let us define what alpha emission is and what beta decay is. So, here. So, alpha particles are released by high-mass, protein-rich, unstable nuclei. So, the alpha particle is a helium nucleus. It consists of 2 protons and 2 neutrons. So, yes. Then it contains no electrons to balance the 2 positively charged protons. Alpha particles are therefore positively charged and are particles that are moving at high speeds. So, that's alpha particles. Now, beta particles are emitted by neutron-rich unstable nuclei. So beta particles are high-energy electrons. These electrons are not electrons from the electron shell around the nucleus, but are generated when a neutron in the nucleus splits to form a proton and an accompanying electron. Beta particles are also negatively charged. Okay, so what does that mean? So let's go here to number 8. we are given polonium-210 and the alpha emission. As mentioned a while ago, alpha particles is a helium nucleus. So we know that the number of protons for a helium is 2. And we know that the mass number is equal to protons plus neutrons. And in a helium nucleus, there are 2 protons and 2 neutrons. So 2 plus 2 equals 4, then there. This is the sign for alpha. So this is rather simple. What you have to do is first put it in this form. So polonium-210. Right down here is the number of protons of that element, and right up here is the mass number. So polonium has a mass number of 210, as mentioned, and it has 84 protons. So 210, 84 p polonium. And we put a little arrow there. Then what we do is we put the alpha emission here, the alpha particle rather here. So what we do is we subtract 4 from 210, which is equal to 206, and we subtract 2 from 84, which is equal to 82. Now notice that the element here has changed. Well, that's because an element varies from its number of protons. So if there's a change in the number of protons, then there will also be a change in the element. So from 84 protons it became to 82 protons, and the element that has 82 protons is lead. So this is the answer right here. So okay, now let's move on to beta decay. So the given is carbon 14. 14 again is the mass number, and beta. And here we have a -1 and 0 beta. So again, what we do is we put first the carbon here. So first with carbon, we put the number of protons here, which is 6, and we put the mass number here, which is 14, and it's a given. Now I put a little arrow there, put in the beta there, 0, -1, and we subtract. So 14 minus 0 is equal to 14, so it still stays the same. Now 6 minus -1 is equal to 7, so we put 7 here. And of course, if there's a change in the number of protons, there will be the element will of course change. So the element now is N, which is nitrogen. So this is the final answer for number 8. Now, these are the final answers for number 8. Okay. Now let's move on to number 9. We're almost done, folks. We're just up to number 10. Okay, number 9. So a sample of radioisotope is found to have decreased from 47 grams to 2.94 grams in 3.3 days. So we have to calculate the half-life. So it's pretty easy. Here we go. Number 9. So we are given 2.94 grams, which is the amount, and we are given the original amount, which is equal to 47 grams. We have the t, which is the time, is equal to 3.3 days, and we are required to find the half-life. So again, we use the formula A is equal to A sub O times E raised to ln1/2 times T over H. Then we substitute the following values into the formula. So 2.94, put it here. 47 grams, put it here. And 3.3, put it here. T there. So again, what you first do is divide both sides by 47. So 2.94 divided by 47. Then we get the ln of both sides. So ln 2.94. ln 2.94 divided by 47 is equal to ln 1/2 3.3 1/2 times 3.3 over H times ln E. So ln of 2.94 divided by 47 is equal to -2.77, while ln 1/2 is equal to -0.693, and 3.3 over H remains the same, and ln E is of course equal to 1. So now we divide both sides by negative 0.6693. There we go. We get the 3.998. Then of course we have to find h, so we put it up here, and 3.998 over here will be divided by here. So h is equal to 3.3 divided by 3.998, which is equal to 0.82525. But remember, we only have to take account for the significant sig figs. So what we do is that go back to the given. Let's see. The lowest number of sig figs is 2, so we should only have 2 sig figs here. So what you do is round up 5, and you get that half-life is approximately equal to 0.83 days. Okay, now we're down to the last number. Number 10. Okay, so here in number 10, the question is that, okay, a sample of radioisotope is found to have a decrease from 11 grams to 0.0859 grams in 1.23 minutes. Calculate the half-life. So again, it's the same problem, different numbers. So if you want, you can pause right now here and try to answer on your own. Okay, let's continue. Let me cover it. Okay, there we go. Okay, for the last number, we are given A is equal to 0.0859 grams. Oh, my bad, gram. The original amount is equal to 11 grams. And the time is 1.23 minutes. So, again, we use the formula. A is equal to A sub O times E raised to ln 1/2 times T all over H. We substitute the following values. So 0.0859, we put it here. 11, we put it here. 1.23, we put it here. Okay. Now first we divide 0.0859 divided by 11. Then we get the ln of both sides. Then the ln of 0.0859 divided by 11 is equal to negative 4.852, which is equal to negative 0.693 times 1.23 all over h times ln E, which is equal to 1. So what we do now is 4.852 divided by 0.693, which is equal to 7. Now we need to find h, so we have 7 here, you put h up here, put 7 down there. H is equal to 1.23 divided by 7, which is equal to 0.1757. So because of sig figs, we have to go back here. We find out that the lowest number of sig figs is 2. So we just need 2 sig figs. So the answer for number 10 is the half-life is approximately equal to 0.18 minutes. Thank you, and I hope you found this tutorial very helpful.